All right, so ready to dive in. Today, we're going to tackle something pretty intense, AP Physics C.
Yeah.
But don't worry, we're not going back to high school exams or anything like that.
Nope.
This is more like a deep dive, like into the really cool world of mechanics and electromagnetism.
Right.
And of course, we've got our trusty guy, the AP Physics C Mechanics and Electricity Magnetism textbook.
Couldn't do it without it.
So just to set the scene, what exactly is AP Physics C?
Well, think of it like this. It's like getting down to the nitty-gritty of the forces that shape the universe.
Ooh, I like that.
Yeah, like how things move, what makes the world tick, and all the mysteries of electricity and magnetism.
Sounds pretty epic. And our textbook breaks it down into two main parts, right?
Exactly. You've got mechanics, and then you've got electricity and magnetism.
Like the ultimate physics power couple.
You could say that, yeah.
Let's start with mechanics then, shall we?
Sounds good.
Okay, so imagine you're at a baseball game and someone hits a home run. How would you predict where that ball's going to land?
That's where kinematics comes in.
Kinematics.
Yeah, it's all about understanding movement, like speed, acceleration, all that.
So, like if you knew the speed and angle of the ball.
Exactly. You could use kinematics to map out its trajectory.
Pretty cool, huh?
Oh, yeah, definitely.
Okay, so we've got things moving, but then we have these things called forces that act on them.
Right.
And that's where Newton's laws come in, right?
They're basically the rule book for how forces work, whether it's a car speeding up or a rocket launching into space.
So those laws are, like, everywhere.
Pretty much, yeah.
That's wild. Okay, so we've got motion, we've got forces, but how do we measure how much effort is involved in all this?
That's a good question.
Right.
Well, that's where work, energy, and power come in.
Ah, those guys.
Yeah, think of it this way. Imagine pushing a car uphill. That's work.
Definitely feels like work.
You're using energy to do it, and the rate at which you use that energy is power.
Okay, I think I'm starting to get it.
Like how fast you can transfer the energy from a stretched rubber band to launch something, that's power.
So work and energy are kind of two sides of the same coin.
Yeah, you could say that.
And power is like how quickly you can flip that coin.
Exactly.
I like that analogy.
Good.
Okay, so what about those moments when things collide, like in a car crash? How does physics explain that?
Oh, that's where momentum and impulse take center stage.
Momentum, right. I've heard of that.
It's basically a measure of an object's motion.
Okay.
And here's the thing, momentum is always conserved.
Conserved, what does that mean?
It means the total momentum before and after a collision, like 2 billion balls hitting each other, stays the same.
So it's like the momentum gets passed from one object to the other.
Exactly. An impulse is the change in momentum usually caused by a force over a short time.
Oh, I see.
That's why understanding impulse is so important for things like designing airbags in cars.
Oh, right, because the airbag slows down the impact.
Yeah, it increases the time over which the force acts, reducing the impact on you.
Wow, so physics is literally saving lives out there.
It is.
That's amazing. All right, let's shift gears a little. Literally, what about objects that spin?
Oh, spinning object.
Like a figure skater, how do they spin so fast?
That's all about rotational motion.
Okay.
And it brings in some cool concepts like angular velocity.
Angular velocity, is that like regular velocity but for spinning?
Yeah, kind of. It's like the rotational equivalent of speed. And then there's moment of inertia.
Moment of inertia, now that sounds complicated.
It's basically how much an object resists changes in its rotation.
So like a heavier object is harder to spin.
Yeah, kind of like how mass affects an object's regular motion.
So if a figure skater tucks their arms in, they'll spin faster.
Exactly, because their moment of inertia changes.
Makes sense. Okay, now for the big one, the force that literally keeps our feet on the ground.
Gravity.
Right? What's the physics behind that?
Well, Newton's law of universal gravitation is pretty mind-blowing.
I bet.
It says that every object in the universe attracts every other object, and the strength of that attraction depends on their masses and how far apart they are.
So that's how we can calculate the gravitational pull between, like, the Earth and the Moon.
Exactly. It's a pretty big deal.
It is. But wait, doesn't Einstein's theory of relativity kind of challenge some of Newton's ideas?
Ah, good point. Newton's theory works great for most everyday stuff, but Einstein's theory is needed when you're dealing with really strong gravity or things moving near the speed of light.
So is it like Newton's theory is kind of wrong?
Not exactly. It's more like Newton's theory is a simplified version.
Ah, okay.
Think of it like Newton's theory is a good map of a city, but Einstein's theory is like a super detailed satellite image.
I see. So it's like zooming in further.
Exactly.
Cool. Okay, we've talked about gravity on a universal scale. Now, what about something more down to earth, like the motion of a pendulum?
Ah, the classic pendulum.
What makes it swing back and forth like that?
That's simple harmonic motion.
Simple harmonic motion.
It's a type of motion where the force pulling the object back towards the center is proportional to how far it's been displaced.
So, like, the further you pull a pendulum to one side,
The stronger the force pulling it back towards the center.
got it. So it's like this constant push and pull.
Exactly. And what's fascinating is that this type of motion pops up everywhere, not just in pendulums.
Really? Where else?
Oh, all sorts of systems, even at the atomic level.
Wow, that's pretty wild. Okay, ready for a bit of a shock?
Haha, always.
We're moving on to electricity and magnetism.
About time.
Right. This whole electricity thing, it's always felt a bit magical to me.
I get that.
What's actually happening when I flip a light switch?
Well, let's start with the basics. Electrostatics.
Electrostatics.
Yeah, think static cling or that little zap you get from a doorknob.
Oh yeah, I hate those.
It's all about electric charges and the forces between them.
So those little sparks are like tiny lightning bolts.
In a way, yeah, it's the same basic principle.
Whoa, okay, and then there's Gauss's law.
That's a good one.
Sounds intimidating, but I hear it's pretty eloquent.
It is, actually.
So what is it?
Well, it's all about electric fields.
Okay.
It basically says that the amount of electric flux through a closed surface is proportional to the charge enclosed within that surface.
That's a bit over my head.
Think of it like a shortcut for figuring out the electric field around charged objects, especially symmetrical ones.
Okay, I kind of get it, but how does all this relate to the circuits we use every day?
Ah, good question. Circuits are like the pathways for electricity to flow.
Right.
So you've got voltage, which is like the pressure pushing the electricity through the circuit.
Okay.
And then you've got current, which is the actual flow of electric charge.
So voltage is like the push and current is the flow.
Exactly. And then you've got resistance, which, as you might guess, resists the flow of current.
So it's like friction for electricity.
You got it.
And all these things work together to power our devices.
Pretty much everything, yeah.
Amazing. All right, time for some magic. Magnets, they have these invisible force fields. But what's really going on?
It's all about the relationship between electricity and magnetism.
Oh, they're connected.
Big time. When electric charges move, they create magnetic fields.
So like even the tiny currents in our electronics are creating magnetic fields.
Yep, even those. And on a much larger scale, the Earth itself acts like a giant magnet.
Whoa, seriously.
Seriously, that's how compasses work.
Mind blown. So what about electromagnetic induction? I've heard that term thrown around.
That's a big one.
What is it?
It's basically saying that if you have a changing magnetic field, it can create an electric current.
So like if you move a magnet around a wire, you can generate electricity.
Exactly. That's how electric generators work.
Wow, that's incredible. All right, we've covered a lot of ground here.
We have.
But I feel like we need to touch on Maxwell's equations.
Oh, we can't leave those out.
Right, they're like the grand finale of electromagnetism.
They're basically the ultimate rulebook for electric and magnetic fields. They describe how these fields are created, how they interact, and how they travel as electromagnetic waves, which include light.
So they bring together electricity, magnetism, and light.
It's a unified theory, yeah.
That's pretty amazing. So we've gone through a whirlwind tour of AP Physics C. It's a lot to take in.
It is.
But it's more than just formulas and equations, right?
Oh, yeah. It's about understanding the fundamental forces that shape the world.
That's what I love about physics, is like this big puzzle.
It is, and there are still pieces missing.
Oh, like what?
Well, we've talked about how electricity and magnetism are connected and how gravity is its own thing.
Right.
But how does gravity fit into the bigger picture? Is there a unified theory that brings everything together?
Ooh, good question. Something to ponder, I guess.
Definitely something to keep those brain cells firing.
Well, on that note, I think we've done enough deep diving for one day.
Haha, yeah, my brain is fried.
Mine too. But hey, that's what makes this so fun, right?
Absolutely. Always more to learn.
Until next time, guys.
See ya.